Hello, everyone. Here's the first concept from the chapter Current Electricity. As you can read from the screen, the formula is V is equal to I into R. There are two ways in which I've tried to show the usage of this result. The one on the left is what we know as Ohm's law, where current is directly proportional to potential difference. And it is a conditional statement. We all know that Ohm's law is valid only when the physical conditions remain constant. By physical conditions, we mean temperature or the dimensions of the conductor or the material of the conductor. And all of these basically point towards the resistance. So only when the resistance of a conductor is constant, we can say that potential difference and current have the direct relationship between them. And we again know that when a graph of V versus I, potential difference versus current is plotted, it turns out to be a straight line for an ohmic conductor. An ohmic conductor is one which obeys Ohm's law. So the point that I'm trying to explain here is that V proportional to I, this statement is only valid when the resistance is constant, and this is what is Ohm's law. So you can see all of that on the left hand side. The one on the right hand side is not what Ohm was trying to say. So this is not Ohm's law, even though this is true practically. And here, if you see, instead of keeping resistance constant, as we saw in the previous case, we've imagined or we've considered voltage to be constant. So we know that if voltage remains constant, the left-hand side of this equation, V is equal to I into R, will remain constant. And in that case, the relationship between current and resistance is an inverse one. That means if current were to increase, resistance would be dropping. So this inverse relation is only applicable when voltage remains constant. This is not Ohm's law, even though it is seen practically. That means it is true and you can be asked questions based on that. And the one on the left hand side is equally true, but that is called as Ohm's law. So in Ohm's law, resistance remains constant and V and I are proportional to each other. Otherwise, if resistance is not remaining constant, even though that is practically true, but that cannot be called as Ohm's law. So what we just discussed, I will try to reveal it practically. As you can see here, there is a wire. This is the enlarged view of the wire in the form of a cylinder. And it is connected to three cells. Each cell has a voltage 1.5. So basically, this is a battery whose voltage or EMF is 4.5 volts. In the initial part of the explanation, I will try to keep resistance constant at 500 ohms. And then I will alter the voltage and you keep a close eye on what is happening to the current. Initially, the resistance value is 500, the voltage is 4.5, and the current, which is obtained by the formula V is equal to I into R, is 9 milliamperes. Now, slowly, I'm going to increase the voltage. So as you can see, now the voltage has become 6 volts, and you see what has happened to the value of current. That has also increased. It has become 12 milliamperes. So even though resistance is constant, if you alter the value of voltage, the value of current will also alter in the same proportion. That means if voltage is increasing, current will increase. And now let me reduce the voltage, see what is happening to the value of current. The value of current is also reducing. It has dropped down to 3 milliamperes. So this, what I've just tried to demonstrate, is Ohm's law. But what is important here is resistance remains constant. Now, I'll try to go to the second part of the usage of the result V is equal to I into R, which I told you earlier is not Ohm's law, but which is practically true. Now, in this case, I will keep voltage constant and I will try to alter the value of resistance. And you will see that current also is getting altered, but in an inverse fashion. So if I try to increase the value of resistance, see what is happening to the value of current. It is reducing. And if I decrease the value of resistance, the value of current will increase. So what kind of a relationship exists between them? It's an inverse one. Graphically, this is not a part of our syllabus. The graph is actually a curve. It's called as a rectangular hyperbola. What we have in the syllabus is just that straight line plot, but that is applicable only in case of Ohm's law, where resistance is constant and V is proportional to I. If voltage is constant and I is inversely proportional to R, that is not there for us graphically. It is only there analytically. That means they'll give you a few values. You will have to substitute and get the answer. Coming back to this slide, let us see the applicability of both of these results. The first one, V proportional to I, where resistance is constant, is seen in case of Ohm's law, as I explained earlier. So any case where resistance is given as a constant, or the graph of V versus I is a straight line, we will have to make use of this relation V proportional to I. On the other end, we have I inversely proportional to R. This is interesting. This also has a lot of applications. This is basically used in all circuit diagrams that involve one cell or a battery. And then there are many other circuit components. And then you've got to find either the current that is flowing in the circuit, or the current that's flowing through every resistor, or the potential drop across each resistor. There, if you remember, the cell or the battery doesn't change. That means voltage is constant. Only in those situations, current and resistance will be inversely proportional to each other. So I will come back to this point when I'll discuss resistors in series and resistors in parallel. In this next slide, I am actually trying to explore the application of the first concept, V proportional to I, that means Ohm's law. As you can see, there are two graphs here, and every year there are questions asked on these graphs. The one on the left has voltage on the y-axis and current on the x-axis, and the one on the right has current on the y-axis and voltage on the x-axis. Both of these graphs have their own names. The first one is called as V versus I. So when they say V versus I, it means V is on the y-axis and I is on the x-axis. And the second one is I versus V for the same reason. And here we are considering ohmic resistors or ohmic conductors. Therefore, you can see that there are four plots, or the four lines that have been shown here. They are basically indicating ohmic conductors. The moment it becomes a non-ohmic conductor, this graph, instead of being a straight line, it becomes a curve. So let's focus on this first plot that is shown by the color red. As you can see, this indicates an ohmic conductor, and there is a point on this graph which is 2,6. So 2 is the value of current in milliamperes. You have to be very careful while reading graphs, especially with the units that have been used. And on the y-axis, we've got voltage, that is 6 volts. Similarly, we have it for the blue graph. Now, the first point that I've tried to mention here is a very important theoretical question. What is the slope of V versus I? That means V on Y and I on the x-axis. The slope is resistance, because when you divide V by I, or when you use the formula for slope, y2 minus y1 upon x2 minus x1, you will get resistance as an answer. This is from the original formula, V is equal to I into R. But if you go to the other graph, where it is I versus V, there the slope is the reciprocal of resistance, and that is called as conductance. Now we all know resistance is the obstruction to the flow of current, and conductance is the assistance to the flow of current. Resistance is measured in ohm, and conductance is measured in ohm raised to -1, which is also called as per ohm, 1 divided by ohm. Now, one question that is frequently asked is, by looking at the graph, you've got to determine which wire has a higher resistance. Now in maths, we've learned a concept of slope. Whichever line has a higher angle of inclination, basically the slope of that line is more. So as you can see here, the conductor that's shown in blue, this is the angle of inclination. And for the conductor that's shown in red, that's the angle of inclination. So the second angle of inclination is more, and we know that slope is tan of the angle of inclination. So if the angle of inclination is more, the slope will also be more. That means the slope of the line shown in red, or the conductor that is shown in red, is more. And for the same reason, even in the second graph, the conductor that is shown in red will have a higher slope. But the meaning of slope is different in both the situations. In the first case, the slope is resistance. That means the conductor shown in red, which has a higher slope, will have a higher resistance. And in the second case, the slope of the graph is conductance. And in this case, the conductor that is shown in red, it has higher conductance. That means the conductor that is shown in blue, it has lower conductance. And conductance and resistance are inversely proportional to each other. So if the conductor shown in blue has lower conductance, automatically its resistance is going to be higher. Therefore, higher resistance in the second case is for the blue conductor, and higher resistance in the first case is for the red conductor. Sometimes questions are also asked on series and parallel arrangements. Now, I will be discussing this in detail later on, but as of now, we know that in series resistance, the overall equivalent resistance, it increases, and in parallel, it reduces. So in whichever case we have higher resistance, that case will stand for series. And in whichever case we have a lower resistance, that will stand for parallel. So here, the wire that has been shown in red, which has a higher resistance, we can say that it indicates series arrangement, and the wire that is shown in blue, that indicates parallel arrangement. And if I go to the second graph, there the statement will become exact reverse. So the higher conductance is for the red one, and therefore the red indicates parallel arrangement because it has low resistance, and blue will indicate series arrangement. One more thing that you will have to be careful with is there can be a question where you've got to take values from these graphs and determine either the resistance or the voltage or the current. In this case, I've given you voltage and current. So basically the question is to find the resistance. So you can see I've used the formula R is equal to V by I, and the value of V is 6 volts. What is important here is the substitution for I. Many students wrongly substitute only 2 without reading the actual unit. The unit here is milliamperes. Therefore, this is 2 into 10 raised to minus 3, and 2 and 6 get cancelled. They give us a 3. And when this 10 raised to minus 3 goes up, it becomes 10 raised to plus 3. That is how the answer in the first case for the red wire is 3000 ohms. For the same reason, the resistance of the wire that is shown in blue is 1500. Now, if I go to the second diagram, there the formula will remain same, but in terms of slope, it is going to be the reciprocal, because here it's I on the y-axis and V on the x-axis. So here you can't say that slope indicates resistance. So if you find slope, you are actually finding conductance. But if I want to find resistance, I will have to take the reciprocal of the slope. Basically, again, I'm using the same formula. R is equal to V by I. You can read the value of V here. It is 4, that's on the x-axis, and I is 2, that is on the y-axis, but it is not just 2, it is 2 milliamperes. Therefore, the substitution is 4 divided by 2 into 10 raised to minus 3, and that is equal to 2000 ohms, or you can also write this as 2 kilo ohms. And with this, we come to the end of the first concept. Thank you.